So the Perutz model is going to be one last equation that's going to really allow us to put lots of stuff that we've already talked about together, see equations that can talk to one another, and fully understand how this process of oxygen delivery, fuel utilization, exercise, CO2 elimination, metabolic acidosis, how it all fits together. So one new equation, one application of something that we've already talked about to sort of tie all of these pieces together. So here's our new equation, okay? And what this kind of shows us, and then I'm going to write this down first and then we'll talk about what this means, is I want you to think about, and this is just a model to help us think about this, that there's a mutual exclusivity with the binding of either oxygen or protons to hemoglobin. So there's a mutual exclusivity of binding oxygen and protons. So binding oxygen and protons. So I want to make sure to highlight that this is not that they bind to the same site. So we don't have oxygen and protons binding to the same site. But this equation is important because it's going to allow us to sort of think about and understand that if we're binding oxygen, we can't bind protons. So that must mean that hemoglobin is deprotonated. Conversely, if we are not binding oxygen, that must mean that hemoglobin is protonated. And we're not going to get into the structural details of where it's protonated, but again, it's not the same site, but this is just a way to allow us to map onto understanding how protonation state is going to affect oxygen binding, and ultimately how whether we're in an acidotic or an alkalotic state is going to affect oxygen binding in hemoglobin. Okay, so putting this together, we know that if we are not bound to oxygen, okay, then we are deoxyhemoglobin, and deoxyhemoglobin is T state. So deoxy T state hemoglobin is protonated, because remember, we're looking at binding one or the other. So if we're not binding oxygen, then we're protonated. But if oxygen does bind to hemoglobin, we release those protons and we have a conformational shift to the R state. And remembering, hemoglobin's a tetramer. There are 4 subunits. As soon as one of them binds oxygen and becomes R state, the other ones all become R state, even if they've not yet bound oxygen. And so then, because they've already changed, they're set up, they're pre-organized, if you will, that they will automatically bind oxygen. So those 4 protomers that we have in a hemoglobin tetramer are either all bound to oxygen or all not bound to oxygen. Okay, so that's that first equation. So let's map on 3 other equations here, 2 that we know of already. Let's talk about our carbon dioxide elimination equation. So we've got water plus carbon dioxide in a reversible process with the enzyme carbonic anhydrase generates carbonic acid. And because of a pKa of 6.35, that weak acid dissociates into H plus and HCO3 minus, okay? So this is our CO2 elimination equation. Okay, so we've got CO2 elimination. Okay, so another equation that we already know about is our fuel consumption equation. So fuel plus oxygen, one-way arrow there, we are not plants, generates carbon dioxide, water, and energy. Okay, so I'm going to use yellow here for this guy. So this equation, right, this is our fuel consumption equation. Okay, so that's our fuel consumption equation. The other piece that I'm going to map on here is highlighting what that energy really is. We know that energy is ATP. So the hydrolysis of ATP is what generates energy, and that hydrolysis ultimately generates ADP plus PI plus protons, and we know that that hydrolysis process generates energy. And we know that energy to be 30.5 kilojoules per mole. So this is the process that happens during exercise. So I'm going to highlight this guy and highlight that this is what is happening during exercise. Okay? So one last thing to map on here, things that we already know about, is the purpose of breathing. Right? Breathing is to bring oxygen in and CO2 out. So what we're going to do here is we are going to map on a whole bunch of arrows that sort of walk us through the flow for how things work here. And I'm going to start right here with oxygen in. And because hemoglobin, when it's oxygenated, is red, I'm going to use red to start here. So when we take a breath in, and again, you're going to have a flip grid assignment that you're going to ask you to sort of think about putting this all together in a video. When we take a breath in, we bring oxygen in. When we bring that oxygen in, that oxygen is going to bind to hemoglobin. So that oxygen binds to hemoglobin. Hemoglobin changes from deoxy T state to oxy R state. Okay, we'll release protons. We'll get to that in a minute. Now that we've got hemoglobin bound to oxygen, it's going to travel through our circulatory system. It's going all the way to the tissues. Remembering with our bucket brigade, what's happening with those respiring tissues is we are delivering that oxygen for fuel consumption. So fuel consumption is going to then generate that oxygen. And importantly, the energy that's generated is going to be ATP. Okay, so that kind of finishes the input route, if you will. Now let's talk about what happens when we've got this CO2 waste. So now we're sort of talking about a return trip. So I'm going to change to blue because what happens in that return trip is we need to not only get that deoxygenated hemoglobin back to the lungs and pick up more oxygen, but we need to deal with this CO2 waste product. So this CO2 waste product is going to find a carbonic anhydrase enzyme that's sort of nearby in the tissues. So in the tissues, this reaction is going to move in this direction, and it's going to generate bicarbonate. So this is the direction that this moves in the tissues. And we're going to generate bicarbonate, and bicarbonate can easily circulate through the circulatory system until it gets to the lungs. And this is an important piece. CO2 elimination requires the use of carbonic anhydrase in the opposite direction. Carbonic anhydrase in the lungs is going to move in the opposite direction, generating gaseous CO2, which can then be breathed out. Wow, so lots of arrows there. So rewatch this if you need to kind of remind yourself of the flow of this. We're actually going to act out this whole process in class where we're going to role play hemoglobin, myoglobin, carbonic anhydrase, protonation state. And the last little piece to sort of map on here, I'm going to change to an orange color here, is how we can think about these processes that generate protons sort of having a feed forward or, a way of sort of directing some additional chemistry here. So hopefully we can see if we are generating protons, if we are making a state of acidosis, that can have an impact on this Perutz model equation. If we increase the concentration of protons by decreasing pH, it's going to push this equilibrium to the left. It's going to push it to the deoxy T state. It's going to release more oxygen. Well, that's consistent with, hey, I'm doing a lot of exercise. How about you give me some more oxygen so I can make some more energy and continue to do more exercise, okay? This protonation state is also going to help direct which way our carbonic anhydrase sort of chemistry needs to work, okay? So we're going to have a lot that we can think about with protonation state induced by either exercise or other mechanisms that generate protons sort of feeding back into this process to allow us to deliver more oxygen to those actively respiring tissues.